Good morning, welcome. Okay, today is a tricky day. As usual, I left in the morning at 6:45, 6:50. My wife was not too well at that time, but things were under control, so I left. And then on the way, I got a call. I was at Tidal Park. I got a call, so I stopped on the side after a bit, and then called back. Things had gotten bad, so she had to get to the hospital. And this is a known problem. Some gastritis related aspects which manifest as diarrhea and vomiting and so on and so forth. So she needed, loss of fluids and things like that. It has been handled in our hospital a couple of times over the past 15, 16 years or so. And so uh, I said I'll come back, and then I realized that I'll have to go and figure out various things in the hospitals there. I have to figure out which hospital also. So said got a emergency part-time driver, and then got the person to drive her here because things are known at least much easier. She's in the hospital now. I was there. I just came to take the class. If I get a call, I'll go out, attend, and then decide on how things go. Okay, please excuse me for today. But till then, it's okay. So I'm playing it by the minute today. Okay, let's continue. We stopped somewhere here. We said thiols are antioxidants. RSH is a thiol. Nice to remember that. Remember that H2S is a thiol. Simplest thiol, R equals H, and that's the nasty chemical, nasty smelling chemical is actually a good antioxidant. It's an antioxidant that is used in the brain and so on. Okay, remember that. On accepting an unpaired electron from another molecule, it becomes a free radical, as you would know, and it so happens that the thiol radicals are far more stable, and thereby they act as antioxidants. Okay. And this is a very standard practice. Whatever is an antioxidant could be a free radical by itself, but it may not be reactive. It can be very stable over sometimes even years and so on, decades and so on, and therefore they act as antioxidants, although it's a free radical. In general, yes. In general, I don't know enough chemistry to give you a convincing answer on that. You need to ask a chemist. If you find out, let me know also a convincing answer. But then again, it's so difficult to predict reactivities based on the principles that at least I know. I've tried, failed miserably. Where I expected something to be reactive, it's certainly not reactive. Where I expected it to be not reactive, it is reactive, and so on and so forth. So I I don't know enough. Okay, and most likely it is known. Most likely all the principles are known. It's just that I don't know. But you need deeper chemistry knowledge to figure that out. It's similar to the hydrogen peroxide and iron. Okay, there the rate is 76 per molar per second. You replace iron with copper, it jumps up to 10 power 3, 10 power 4, whatever. So I don't know the exact reason. That I'm sure that is understood, but I don't know the exact reason. Okay. So this is the thiol reacting with hydroxyl radicals to give you a thiol radical, which is more stable, and water. RS dot is the thiol radical. It's nice to remember this name. And we are going to spend some time with the thiol radicals because they happen to be rather common and important, typically as an antioxidant and so. Another example, thiol, RSH interacting with the peroxide, giving you the thiol radical again, and the carbonic acid. Fine, these are just examples. You can look through these if you want. You can write them down, but not just a glimpse of them is good enough for this course. The reactive species abstracts a hydrogen atom from the hydrocarbon chain of a fatty acid residue. You have the cell membrane, right, a bilayer of lipids, or any layer of lipids, even a single layer in vesicles and so on and so forth. The reactive species, excuse me, the reactive species can abstract a hydrogen atom to leave this, okay, leave this back on the lipid membrane, right. So, this is a triple bond C and a lone electron, an unpaired electron, and it happens to be reactive. Okay, this is highly reactive, and since this is, there is a electron, extra electron here, it is reactive. It is going to give those electrons away to other things and so on and so forth, and cause a kind of a chain reaction, which is going to cause damage. Okay, one of the reasons how hydrogen abstraction from hydrocarbons in the fatty acids of a membrane can cause significant damage. Okay, well known chain mechanism. Let's continue here. This is a slightly different context. This abstracts a hydrogen atom to leave this behind. That free radical can interact with RSH as follows. RSH is our focus here. So, RSH plus this free radical, which remains on hydrogen abstraction, leads to the thiol radical. Okay. And of course, you get back this, but the damage is done. Okay. So, this is some reactions that happen which have significance and so on and so forth. Whenever there is a need, you can go back and check the exact details of the reaction. The thiol radicals that are formed when some metals react with the thiol radical. For example, when ferric ions react, you get the thiol radical with the thiol. Copper, same effect, and so on and so forth. Okay. So, when metal ions interact with the thiols, you can get a thiol radical. And thiol radicals can also be formed by homolytic fission of the disulfide bonds in proteins. You know that SS is the disulfide bond which gets formed in proteins and so on and so forth. You break it cleanly, homolytic fission, then each one takes an electron and becomes a free radical. You get two free radicals, right. So, for example, cysteine, which can form a disulfide bond with another cysteine, if it undergoes homolytic fission, then you get two thiol radicals. You have cysteine S dot, the R is cysteine here, and two of those molecules. Okay. This reaction, okay, let me give you some time. This reaction has a lot of relevance in spoilage of flour, the milled flour. Okay, that is, you have all these flours, wheat flour and so on and so forth, right. The milling is flour milling. There is a lot of energy that gets into that gets added on to the material to for the grain to become flour. Okay, so that energy is good enough to cause homolytic fission. Okay, so cysteine thiol radicals are formed, and that abstraction causes a chain reaction which can cause damage to the lipids and thus the flour. Okay. And it's good to note that all food is cells, biological cells. So, anything that destroys the cell will destroy the food. Today is what, 15th Feb, is it? Okay. Jai Shri Abbas is here. Jashwin, Manisha is Praveen, Raghavi, Swati is there. Vikash is there. Wow, full house, very nice. Good. Another example, thiol radical and ascorbate, which is an antioxidant, vitamin C. So, this is the thiol radical GS dot ascorbate represented as AH minus, okay, it is a negative ion. So, it gives you a GSH and this radical, okay, ascorbate radical. The rate constant is quite high, 5 into 10 power 8 per molar per second. Just get an idea, okay, I do not expect you to remember any of these. Now, thiol radical also reacts with NADH or NADPH to yield the NAD radical, and therefore, this is one of the reactions that you might want to remember. GS dot thiol radical interacts with NADH to give you NAD radical, which is rather a powerful radical. Yeah. GSH is what we started out with, right here, cysteine. So, yeah, interchangeably, yeah, you can take one for the other. G is more specific for a particular thing. These are all G related aspects. Okay, that is also 10 power 8. Okay. So, you get an idea of some of these radicals, some of these reactions, and the rate constants associated with those reactions. Good. Now, some involved detail. What happened with, where does that come in? Okay, that comes in later. There's some more part of the story which I think will come in the termination reactions. Don't worry. Okay, fine. So far so good, and that's good enough, right? You can just look through it, and or you have been exposed to a few reactions, which is the essential idea here, nothing more. Whenever there's a need, you go and refer to books, papers, and so on. And the next obvious thing is termination reactions, but before we get into that, there is one type of reaction that I'd like you to refresh your memories on, if you remember it, or pay attention to, which is called a dismutation reaction. Do you remember what this is? I'm sure you'd have heard this. You remember? Very nice. You're into chemistry then, good. Which is nice. Each one has a certain orientation, good to know your orientations, which means these are the things that indicate orientations, okay, your readiness to jump into it, look into it, and so on. So, what is a dismutation reaction? Even if you recall it incorrectly, doesn't matter. Exchange has so many different meanings, especially with systems biology. Exchange has a totally different connotation. Well, you can view this as some exchange, but I don't think it's considered an exchange reaction. A dismutation reaction is a reaction in which the same species gets both oxidized and reduced. Okay. So, the species is dismutated, it gets both oxidized and reduced. If you didn't know it, it's good to know it. If you just forgot, doesn't matter. This is what it is. For example, if superoxide gets dismutated, what do you think will result? You've all gone through our 4 major reactions. You can look through those reactions also. Okay, look through those reactions and guess what are the products if superoxide gets dismutated. I gave you a hint also, right? Those 4 reactions with oxygen and so on and so forth. 1 electron reduction, 2 electron reduction. So, what would happen? Any guesses? What up? Yeah, what's your guess? Both O2 and peroxide will form one, yeah, oxygen, right? Yeah. So you get oxygen, which is one form. It's the oxidized form of superoxide. Okay, superoxide has one extra electron. In terms of electrons, loss of electrons is oxidation. If it loses an electron, it becomes oxygen. If it gains an electron, it becomes hydrogen peroxide. So you get both oxygen and hydrogen peroxide. Of course, they're happening to two different molecules. But the same species gets both oxidized and reduced, right? So now you can connect it to superoxide dismutase, which is the antioxidant enzyme specific for superoxide. So why is it called dismutase? You can figure out. Okay, so that's a dismutation reaction which you should be familiar with. Okay. So the superoxide dismutase enzyme, by the way, superoxide dismutase has many forms: a copper form, a zinc form, a manganese form, and so on and so forth. So in this case, a copper form can mediate this dismutation. The oxidation reaction is to separate it out, to just to highlight the oxidation. You get the enzyme superoxide dismutase plus the superoxide giving you oxygen, whereas the same thing could also result in hydrogen peroxide, okay, with of course the addition of 2H plus and so. So that is how the superoxide dismutase works to negate superoxide. Okay, so we are pretty much done with propagation reactions. We saw some examples in the context of propagation reactions, where you have free radicals both as reactants and as well as products. Termination reactions, quite obvious, they terminate free radicals, right? You have only the free radicals only on the reactant side and none on the product side. Easiest, the termination of two hydroxyl radicals to give you hydrogen peroxide, straightforward. And do you recall the enzyme that does this? Pardon? No, I briefly mentioned this. Catalase, no, catalase interacts with hydrogen peroxide. It's easy to measure. At one point in time, we are so used to measuring catalase and SOD that we are measuring catalase and SOD. And very nice, very nice. Okay, it's glutathione peroxidase. Okay, because peroxide is formed there. Glutathione peroxidase is specific for hydroxyl radicals. That's an enzyme that's specific for hydroxyl radicals. So remember that. Glutathione peroxidase for hydroxyl, superoxide dismutase for superoxide. Okay, catalase for hydrogen peroxide. Okay, yeah. When we were doing this correlation between antioxidant, the reactive species and its antioxidant levels, we were so used to getting data on catalase. The catalase was run of the mill for us. We always characterize catalase. So there were early attempts to link catalase and hydrogen peroxide, catalase and hydroxyl radicals, superoxide and superoxide dismutase. And of course, there was no correlation there also. I was very happy until one fine day I realized, how can I relate catalase and hydroxyl radicals? I missed it for many months. And then we completely took out that data from making the point of, because the point had to be made very strongly that there is no correlation between reactive species and its own antioxidant, right? Where you expect a certain relationship, that doesn't happen. So to make it strongly, we just took out that data. There was no correlation between those also, by the way. But anyway, the catalase works on hydrogen peroxide directly. It breaks down hydrogen peroxide. This is 5 into 10 power 9. Now you see the rate constants inch up by orders of magnitude. Termination reactions are typically fast reactions. If the rate constants as high as this, one radical can be used to scavenge the more dangerous radical typically if there is a need. Two examples: nitric oxide NO dot, which is a common free radical in human systems, biological systems, can be used to negate hydroxyl radicals, which is a more toxic radical, because the rate constant is greater than 10 power 10. So, you use one radical to take care of the other radical. Okay. And another example, nitric oxide again takes care of peroxide, which is not as bad as hydroxyl, but still quite bad, to form peroxynitrite, and this is HNO2. Here the rate constant is greater than 10 power 9 per molar per second. And a very standard technique that is used in some analysis techniques which are well known, and even while manipulating systems you could use this if there is an appropriate need for that. Today all are present, so I'll just run this. Excuse me. Nitric oxide is an important reactive species, important free radical. It has multiple physiological roles in vascular and nervous systems especially. For example, nitric oxide synthesized by the vascular endothelial cells that line the interior of blood vessels. Vascular endothelial cells that line the interior of blood vessels. The nitric oxide reaches the underlying smooth muscle by diffusion from the vasculature. It binds to guanylate cyclates and activates it, and so on and so forth. So, a lot of things happen because of that. This is an important step in the process, and nitric oxide is a well known reactive species in human systems, many systems, many biological systems. This results in more cGMP production, which lowers intracellular calcium and relaxes the muscle, dilates the vessel, and thus lowers blood pressure. One of the mechanisms of nitric oxide action, which is well known. Any questions or comments so far? I need a let me keep it open. Right. Okay. This is the story that I thought was coming up there. I forgot it was termination. GS dot plus GS dot giving you GSSG. It has a very high rate constant, 10 power 9, right? And GSSG is formed in the cell, it is known. And people assume that this is the mechanism by which it happens. GS dot, we saw GS dot forming in various different cases. People thought that this was the mechanism by which it happens. However, so this is thiol radical annihilation by dimerization, obvious. Rate constant is high and therefore, it is assumed to happen in the cell. But this is not common inside the cell. This particular annihilation is not common inside the cell, because the intracellular concentrations of the thiol radical GS dot is very low, and therefore, they don't the possibility of them coming together, which is the basis of all reactions, is very small. Okay. But GSSG is found in the cell, thiol radical gets eliminated in the cell, and so on and so forth. And they later found out the mechanism by which it happens, just for information, is through this GSH glutathione is present in millimolar levels in the cell. Millimolar is huge, right? You can work out the number of molecules, you will know the hugeness of that number. Millimolar levels in the cell. And also the pKa of the thiol group of glutathione is 9.2, okay, which means that physiological pH is about 1 to 2% ionized. at 7.4. So, it exists in this form. Glutathione exists in GS minus and H plus. And this GS minus can interact with the thiol radical to give you GSSG dot minus. And this is how the thiol radical usually gets handled in the cell and not by the dimerization. Okay, although dimerization is a very fast reaction and so on and so forth, also look for the amounts that are there to get better insights into the reactions happening in the cell. Any questions on this? So that's 10 power, this is not small either, this is 10 power 8. That's 10 power 9, this is 10 power 8, 8 into 10 power 8, that too, very close. GSSG radical happens to be a good reducing agent. It has a reduction potential, standard reduction potential of minus 1.5 volts, and therefore it can easily donate electrons, and therefore it's a good reducing agent. And this, it can even reduce oxygen to give you the superoxide radical at 10 power 8 per molar per second. Okay. I don't want to bore you with this reaction after reaction. Whatever was important enough in the overall context, I just picked up and presented that to you. But that's only a very, very small fraction of reactions. Okay, remember that. Okay, just to get an idea. Whenever there's a need, you go and check up whatever reactions you want from appropriate sources. Towards the end of the course, we'd look at more reactions in a somewhat comprehensive framework when we get to it. I'll just briefly mention that.